And we'll talk about chapter 6. This is the last chapter that's going to be on exam 2. And just to get it on the recording, I'll repeat. Next Friday, March 3rd, I will not be here. So don't come to class. That'll give you an extra week to get some things done and turn it in before the midterm grades are due on March 6th. And then we'll come back on the 10th of March and have a review of these 3 chapters. Plus, I probably ought to hand out the next lab because we'll be doing the next lab the week I come back on detecting signs of chemical change. So I'll hand that one out during lab time. Okay, chapter 6. There we go. So we've made some progress up to now. We've learned how scientists think, sort of, how we make measurements. We've learned the chemical symbols and what all the numbers mean. Most of the numbers. We've learned what the atomic number means. Now we're going to learn how to use some of that information and follow the progress of reactions from reactants to products in terms of both how many atoms and molecules are interacting, and use that information to determine how much mass is going into the reaction, how much is coming out, and where. Right? We already know that the mass going in has to be the mass coming out. Lavoisier proved that long time ago, before he lost his head. So let's get on with it. How do we determine the, let's see, I guess in chapter 5, we did go through, let me go back to my hard copies so I can get my bearings. I teach too many courses. I kind of lose where I'm at. So chapter 5, we've done bonding so far. Okay. All right. All right. Each one of the elements in the periodic table has 2 important numbers there. One, of course, is the atomic number, which is the number of protons for each of the atoms. It doesn't give you the mass number, that is the number of protons plus the neutrons in most periodic tables, but it does give you the atomic mass. There's a difference between mass number and atomic mass. Atomic mass is the average, is the weighted average of masses of isotopes. We covered isotopes, didn't we? Right, different numbers of neutrons, same number of protons. Okay. So if you take a weighted average, the atomic mass is the weighted average of all those isotopes in a naturally occurring sample. And that value will be one of those numbers in the periodic table up on the wall. It's in the upper left-hand corner. And they'll always be decimals. There'll always be a number, point, something, 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 because they are weighted averages. They'll never be whole numbers. There's only one whole number associated with any of the elements on that table, and that's the reference element, the reference isotope. carbon 12. Carbon 12 is given by convention. It's given on out atomic mass units per atom of that isotope. And that's what everything else is based on. So not even carbon up there will have a whole number 12 because there are other isotopes of carbon that have to be averaged in. Okay. So we can, if we want to know the mass, the average atomic mass of an element, we just read it off the table. But if we want it for a compound where we have several different elements together, all we have to do is add up the individual atomic masses for all the elements and treat them individual atoms. So here our example is tin-2 fluoride. Tin-2 fluoride says that you've got one atom of tin, which is 118.71 atomic mass units, and you've got two fluorines. Each one of those is 19. So you just have to multiply that by 2 and add them all together. And for that formula, SNF2, you have 156.71 atomic mass units. You can do that for any formula. It can be an ionic compound where it's the simplest whole number ratio of the elements. Remember, ionic compounds don't exist as molecules. They exist as crystal structures. And the simplest whole number ratio is what we're actually reporting in the formula for the compound. But for molecular compounds like water, carbon dioxide, they are individual molecules. So when you see those formulas, you know that that's the formula for an individual molecule that has independent behavior. Now, how do you know the difference? Well, the ionic compounds are going to be a metal and a nonmetal, always. And the molecular compounds are going to be two nonmetals, right? Because they share electrons. So they form those independent units, whereas ionic compounds are just an accumulation of positive and negative charges. So you could have a real tiny salt crystal of sodium chloride. You can have a big salt crystal of sodium chloride. There are no individual molecules in there. They're all ions. So NaCl is the simplest whole number ratio of those. And that's the way the formula is reported. So what's the formula mass of H2SO4? What is H2SO4? What's the name? Starts with an H, right? So it's an acid, right? That's some kind of acid. So if the formula is this, then we say, all right, is there oxygen there? Yeah, there's oxygen. So we don't start with hydro. Remember those rules? Don't start with hydro. You start with whatever that is, right? And that polyatomic ion is sulfate. And H become X. So it's sulfuric acid. Okay. That's not part of the question, but I thought I'd throw that in there anyway. So two hydrogens would be 2 times 1.01 atomic mass units. Okay, just look at them on the table. I always round to 2 decimal places. Sulfur is, let me see if I can't remember that one too much, 3206. We've only got one sulfur. And we got 4 oxygens. And rounded to 2 decimal places is 16. Okay, so you just multiply, 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 and add. And you should end up with something in the neighborhood of 98. Let's see. Won't be exactly 98 the way I've got it listed here, because we've got these 0.01 and 0.06, but it'll be close. Now, we defined what an atomic mass unit was, didn't we? When we were talking about individual elements and isotopes. Yeah, I know we did. An atomic mass unit is roughly the size of one proton. So that's why hydrogen is essentially one atomic mass unit for its mass, except for the other isotopes that kind of skew it up a little bit. Okay. So what we're saying is that collection of atoms has a mass of 98 atomic mass units. And that carbon as our basis, that carbon isotope has exactly 12 atomic mass units for its mass. That's our reference. But atomic mass units are not useful in the laboratory. We don't have any balances that read off in atomic mass units, because an atomic mass unit is useful for only one formula or one atom. And when we put something on the balance, we've got billions and billions of atoms. So we need another unit. So we introduced this unit called the mole. And that's not the little furry creature that digs up your front yard. In chemistry, the mole is just a number of things. Now, there's an analytical reason that it is that number, right? But we don't have time to go into that right now. We just have to accept the number as true. And 1 mole of something is determined periodically by people who do this for a living out to like 20 or 30 decimal points. But we don't need that accuracy. All we need is this one, 6.022 times 10 to the 23rd things equals 1 mole. And we abbreviate mole by just dropping the E. That makes a lot of sense, right? Why not just put the E on there? I don't know. So this could be atoms. Would be that many atoms would be 1 mole. It could be molecules. Right? It could be formula units. If it's an ionic compound, right? We have formula units. Or it could be, I don't know, it could be chickens. You could have a mole of chickens if you had that many of them. Okay, it's just a number as far as we're concerned. Now, by definition, they're saying that if you have that many atoms, 1 mole of carbon-12, it will weigh exactly 12 grams. Okay. So that's convenient. That's good for us, because now instead of reading those numbers, atomic mass, off of the periodic table, naturally occurring carbon would be 12.01 grams per mole instead of 12.01 atomic mass units per atom. Then now we have something we can grab onto. We can now convert between numbers of atoms, numbers of molecules, numbers of, I left off ions, numbers of ions, and what that equals in mass. Okay, so if we have 1 mole of calcium atoms, then that will weigh 40.08 grams. Okay. And notice from earlier chapters, if you have an equivalence here, what does that mean? We have a conversion factor, because that equals that. So if we have a conversion factor from this relationship, and we have, we weigh out so many grams of calcium on the balance, we can convert that many grams to how many moles it is. So we can relate the mass to the moles now. All right, so there you have a mole of eggs. What I'm saying is that this relationship tells us the molar mass of calcium. Right? So calcium, the molar mass of calcium equals 40.08 grams per mole. There's your conversion factor, right? And remember, all conversion factors are equal to 1. So if you need to cancel the grams and give you moles, you just put the grams on the bottom. If you want to cancel the moles and leave you with grams from whatever value you're starting with, then you leave it like it is. So our examples here, did you sign in? Okay. What's your name again? It was her car. They said they saw your car out there. So now, the way we added up those atomic mass units for our formula before, do the same thing for molar masses. If you want to know the molar mass of a compound, you add up the molar masses of all the elements that are in the formula. So in this case, carbon dioxide, you just need 1 carbon at 12.01 grams, right here, and 2 oxygens at 16.00. And you have carbon dioxide then has a molar mass of 44.01 grams per mole. And there you have a conversion factor for the compound as well as just elements. All right, so let's use that knowledge and solve this problem. What's the mass in grams of 2.5 moles of ethane? So we're starting with 2.5 moles of ethane. So what do we need? Well, the question is, what's the mass of that many moles? Right. So here's where we're starting, there's where we're going. We need a conversion factor that will cancel moles and leave us with grams. Okay. So whenever you see grams and moles in a quotient relationship like this, always think molar mass. So we just need to add up 2 carbons, 2 times 12.01, and 6 hydrogens, 1.01, right? So let's see, that first one is 2402, right? 24.02. And then the bottom one is 6.06. That's 30.08. 30.08 grams per mole. So we got grams on the top, moles on the bottom. We just put it in like this. That moles cancel. And now, like I always say, that's the thinking part. The rest is just crunching numbers. So we'll take 30.08 and multiply times 2.5. Well, let's see. That's what my calculator says. But they only gave us 2 significant figures here, didn't they? So we have to round it to 75. Because that's a multiply divide rule. Okay. So I bet you thought you'd never use dimensional analysis again, right? Nope. It's buried in the system, sorry. And the reason we're going to need to be able to do that is because when we solve problems using balanced equations, we need to be able to convert backwards and forwards between mass and moles in order to use the balanced equation to say something about what's happening. We're going to get there. How about the number of moles of 50 grams of water? There we have 50 grams of water. So that's where we're starting. And we want to know how many moles. Right. So we need a conversion factor that will cancel grams and leave us with moles. So what's the molar mass of water? Well, 2 times 1.01 for the hydrogen and 1 times 16 for the oxygen. That's 18.02. Okay. So we divide 50 by 18.02. And we get 2.7747. We've only got 3 significant figures. Right? So we have to round it off. 2.77 moles. And notice that, just a reminder, conversion factors are exact numbers. They have no bearing on the number of significant figures in your answer. So you can have a string of 10 conversion factors. The only one you need to concern yourself with is the first one. So this one has 3 in a multiply divide situation. So the answer has 3. All right, they rounded up. Why did they round up? Did I calculate it correctly? Let me check it. Do 50 again, 18.02. No, that's wrong. Should be 2.77. Let me make a note. Let's see, where am I? Here it is. This needs to be 2.77. Okay. We can do that for aspirin. Does anybody take aspirin anymore? I take a baby aspirin every day, but not for headaches. It's to keep my platelets from sticking together. I think that's 81 milligrams, isn't it? It's a baby aspirin. Whereas the aspirin that we used to have when I was a kid, that's all you had. If you had an ache or a pain, just give them aspirin. It was 325 milligrams per tab. And you wanted to swallow it quick because they weren't coated. And if it started to melt on your tongue, it tasted horrible. But aspirin has a molecular formula of CH203 EXAM2. So how would we calculate the molar mass of aspirin? It says, what's the mass of 1 mole? That's molar mass. 9 times 12.01, right, for carbon. 8 times 1.01 for hydrogen. And 4 times 16 for oxygen. And it turns out that's 180 grams is the molar mass of aspirin. All right. So when we write a chemical formula, what are we saying? Well, it depends. It depends on whether it's an ionic compound or a covalent compound. If it's a covalent compound, we're saying that's how many atoms of each element is in the molecule, that independently circulating whatever. If it's a ionic compound, we're saying that's the simplest whole number ratio of ions in the compound. So in this case, we have N2O4, 2 nitrogens and 4 oxygens are present in that formula unit. That was the microscopic view. The macroscopic view is something that we can get hold of. In other words, we can measure the mass of it. We have enough of those atoms to make a mole. So what we're saying is that 1 mole of these molecules, N2O4s, is what we now have, and we can say something about that. We have 2 moles of nitrogen and 4 moles of oxygen, right? So for every 1 mole unit of N2O4, you have 2 moles of nitrogen, 4 moles of oxygen. Let's see, how many moles of carbon atoms and hydrogen atoms are present in 2.5 mole sample of ethane? Well, let's see, is it animated? Yeah. 2.5 moles of that formula unit says that for every 1 mole of ethane, you have 2 moles of carbon. So we actually have 5 moles of carbon atoms, and we have 15 moles of hydrogen atoms. That's aspirin again, isn't it? C9H8O4. How many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? In 1 formula of aspirin. Okay, so we have 9 carbons, we have 8 hydrogens, and 4 oxygens, moles of oxygen. Right. My guess is that, well, you can calculate exactly how many atoms there are, but you need Avogadro's number. That's what 6.022 times 10 to the 23rd. It's also called Avogadro's number. All right. So this came out of your textbook. If you'd like to use this type of flowchart arrangement, sometimes I used to use flowcharts in the lab, but I never used them for doing calculations like this. I always use flowcharts to coordinate activities in a procedure. If I had an analytical procedure that had to get to one point on one path before I could get there with the other one, then it was a matter of timing. It's kind of like cooking, right? Some things cook faster than others, so you start the one that takes the longest first, and then at a certain time, then you start the next course, and then they're all ready at the same time. That's what flowcharts are for me. But you can use this flowchart if you want. I think dimensional analysis works better. In other words, where are you starting? Where do you want to end up? If it's a calculation, what intermediate steps do you need to get there? Right. You have what you're given, you have your target, and then you have a conversion factor or multiple conversion factors. You have to chain them together. All right. So it seems like we've done this before. If I'm driving from Beckley to Atlanta where I have family, did we do that before? When we were talking about dimensional analysis? Yeah, we don't have to stop here. You just need to know how far is it, right? And what's your mileage on your car? That's how much gas you need. And then what does gas cost? And that'll tell you how much money you need to get down there. And then you double it to get back. And then you maybe pad it with 10 or 15%, maybe 20% in Atlanta to get around. Okay. Which one is closest to the average mass of 1 atom of copper? I don't know why I keep this slide in here, because you can use logic and figure out which one it is. All right. Is 1 atom going to be 60, 50 grams? No, they're not that heavy. So the answer has to be E. But how would we solve it? Let's see, it didn't do it. Okay. So let's say we have one atom of copper. One atom of copper. And we want to find out what's the mass of that copper. Well, we can't go directly from one atom of copper to mass in grams. The only conversion factor we have available is molar mass. So we got to find out how many moles does that represent. Right? It's going to be a fraction of a mole, isn't it? Avogadro's number, 6.022 times 10 to the 23rd atoms, 10 to the 23rd atoms, a mole. That way the atoms cancel and leave you with moles. Now, we know the relationship of moles to grams. We just have to look it up on the table. Copper is 63.50. Getting a glare. 55. 63.55 grams per mole. Moles cancel. Now we're left with grams, just like we wanted. And we do that calculation, and it should come out to 10 to the minus 22 grams for one atom. Okay, dimensional analysis. Got it? Okay, okay. All right. What's the number of copper atoms in 63.55 gram sample of copper? Right. We just determined the molar mass of copper is 63.55 grams per mole, right? So if you have that mass of copper, you have 1 mole of atoms. Well, if it says what's the number of atoms, what is 1 mole equal to? 6.022 times 10 to the 23rd. So you actually have that many copper atoms if you have measured 63.55 grams of copper. So if we have 3 samples, let's see, A, B, and C. First one is magnesium, is it? Yep. Second one is zinc. And the third one is silver. And you have 100 grams of each one. 100 grams. Okay. Which one of those has the greatest number of atoms? Right? How many atoms would it take to get to 100 grams for each one of these? Well, what's the molar mass of each one? That's where I would go. Magnesium is about 24.31. Zinc is 65.39 grams per mole. And silver's big atom, 107 point. I need a bigger chart. 107.87. Okay. So what that says is, for the same number of atoms, it only takes 24 grams of magnesium. And it takes 65 grams of zinc and 107 grams of silver. So if you got the same mass of each one, which one would take the most number of atoms to make up that 100 grams? The one with the lightest atom, wouldn't it? If your atoms are lighter, it takes more of them to make up 100 grams. So magnesium would be the one with the most number of atoms in that 100 gram sample. Okay. All right. So I'm going to leave that up there because we've got silver, zinc, and magnesium for the next one. Put them in a different order, but the same ones. Silver, zinc, magnesium. Now we have a different mass for each one. 107.9 for silver, 70.0 grams for zinc, and 21 grams for magnesium. Now we want to put them in descending order of numbers of atoms. So what you'd have to do here is do a calculation, right? How many moles of each one do you have? Well, since we've only got 3, I suggest that we not go to the trouble of calculating each individual one exactly. All we have to do is put them in order. So let's say, what's their relationship to a mole? 107.9 grams of silver, that's equal to 1 mole, isn't it? Right? How about zinc? That's greater than a mole. And 21 grams of magnesium is less than a mole. So now we can put them in order from descending number of atoms, greatest to least. Greatest number of atoms will be more than a mole. And then the next one would be 1 mole. And then the last one would be less than a mole. So there should be zinc, silver, magnesium as our order. And BAC is that order. All right. Now there's a review document for this chapter also. Well, actually, the review document covers all 3, I believe. Yep. So there are lots of these little problems in there just like this that you need to practice. And if that's not enough, there are Brightspace practice tests in this module that you can go in and drill yourself, and it'll treat it like an exam and grade it and tell you which ones you got wrong. You can focus on where you're weak. There's also for this review document for chapters 4, 5, and 6, there's a key in Brightspace for that review document also. I didn't print it out, but it's in there, and you can check those answers against that key. For this one, say you have a 100-gram sample of each of the following. Rank them in descending order of number of oxygen atoms. Okay, that sounds like a big problem, but if we're methodical about it, we just need to put water, nitrous oxide, water, nitrous oxide, C3H6O2, C3H6O2. I'll be willing to bet that's propionic acid. And then CO2. Okay, we've got 100 grams of each one. 100.0. We want to throw away a decimal when I don't have to. Okay, this is where I invoke the memory of Henry Ford, the assembly line. You're going to do the same calculation for each one of these, except there will be minor changes. The steps will be the same, but there'll be some significant changes in between that are characteristic of that molecule. But the steps are going to be similar. All right, so what was the question? Descending order, number of oxygen atoms. That's what we're looking for. Number of oxygen atoms. Right. So we need to find the number of molecules first, because we have a weight, a mass for the molecule. And then we can use the ratio of the number of oxygen atoms in the molecule to determine how many oxygen atoms there are. Now, since we're putting these in order, we don't have to go all the way to the number of oxygen atoms. We just go to moles. We can compare using moles because it's a unit of measure of numbers. Okay. So what we need here is something that will convert grams into moles. Okay. Water, we did that one earlier. Molar mass for water is 18.02. Okay. 16 plus 2.02 for the hydrogens, 18.02. N2O, we have to calculate that one. N2O will be 2 times 14.01, right? 14.01 times 2, then plus 16. Times 2, and then add 16. 4402. Now notice I've got these. We want to get rid of the grams and leave us with moles. That's why the grams is in the denominator. This one we need 3 carbons, which is 12.01. Right? And 6 hydrogens, which would be a total of 6.06. And then 2 oxygens, which will be 32. Right? 16 times 2. 7409. And then carbon dioxide. So we got 1 carbon, 12.01, and we got 2 oxygens at 32. That's 4401. There we go. So those are our conversion factors to moles. We got rid of the mass, and now we're talking about numbers in terms of moles. But that's moles of a compound. We want moles of oxygen. So we need one more conversion factor. We want the number of oxygens per compound. Okay, how many here? For each compound, we got 1 oxygen, right? For water. For a dinitrogen monoxide or nitrous oxide, laughing gas, we got 1 oxygen per molecule. How about propionic acid? We got 2 oxygens per compound. And CO2, we have 2. Right? So that takes out the compounds and leaves us with oxygen. Now we can calculate the moles of oxygen in each one of these samples and put them in order. So we got 100. Oops, that's too many. There we go. Divided by 18.02. And that is 5.55. Let's see, we got 4 significant figures. 5.549. And that's moles of oxygen. The next one is 4402. Divided into that and times 1. So it's 2.272 moles of oxygen. For this one, 100 divided by 7409. But we have 2 oxygens for that many moles of compound, so we have to multiply by 2. 2.699. And the last one, 44.01 times 2. 4.544. There we go. Moles of oxygen. Now we can put them in order. Right? So what's number 1? Let's see. Descending order. So which is the greatest? That one right there. So that's number one. The next one is this one. The next one is this one. And the last one. Okay. Oh, I animated this one. Okay, so there you have it in black and white type. There we go. Now we can put them in order. Water first, carbon dioxide, propionic acid, and nitrous oxide. Seems like a lot of work just to get that one answer. But if you do it like Henry Ford, set up your assembly line, then you check yourself, say, okay, are these steps right for that one? I'm sure they're right for that one. They got to be right for the rest of them. You just change this value here and this value here. Okay. Calculate the number of molecules in 0.325 gram tablet of aspirin. All right, I'm not going to do that one on the board because it's right there. Now, why did we use 0.325 grams? Right, on the previous slide before this, we had 325 milligrams, didn't we? 325 milligrams is 0.325 grams. We have to use grams because the conversion factor is moles per gram. And the question asks us how many molecules, so we have to use that molar mass. That cancels grams here. And once we have moles, we can convert moles to numbers of molecules. Now they chopped off a 2. I wouldn't have done that. And that gives us 1.09 times 10 to the 21st molecules in one tablet of aspirin. I think is that 5 grains? Pharmacists used to measure stuff in grains. And then they switched sometime in the past. I don't know when it was. All right. So now that we know how to do this, we're going to talk about chemical reactions. Writing the chemical reaction, balancing the equation, and doing something with it. Actually solving a chemical reaction problem once we get the balanced equation. First is the way that the equations are written. Reactants are always first on the left. We go left to right. So we write whatever the reactants are, separate reactants, calcium sulfide plus water is, in this case, are the reactants. And then we have an arrow to the right that says when those two react under the conditions that are defined for this reaction, we get calcium oxide plus hydrogen sulfide. Those are the products. Okay. First thing you have to do when you write an equation, especially if the word problem names the compound. If it names the compound, then you've got to write the formula from the name. Right? That's why we spent so much time on naming compounds. Then when you balance the equation, an equation is only balanced when you have the same number of atoms of each element on the reactant side and the product side. In this case, we've got 1 calcium on the left and 1 calcium on the right. Now that can be, you can look at that as either 1 calcium atom or 1 mole of calciums. It doesn't matter. For balancing purposes, either one works. You've got 1 sulfur on the left and 1 sulfur on the right. You've got 2 hydrogens on the left and 2 hydrogens on the right, and 1 oxygen on the left and 1 oxygen on the right. So this equation is balanced the way it's written. We didn't have to do anything special. What that says is 1 mole of calcium sulfide plus 1 mole of water yields 1 mole of calcium oxide plus 1 mole of hydrogen sulfide. Now, if we have to make changes to the equation so that we have the right number of atoms of each element on both sides, once you have written those compounds, you cannot touch the subscripts. They're sacred. They're chiseled in stone. The only way you can balance the equation after you've written the compounds correctly is with coefficients. That is, numbers in front of each one of the compounds, or elements. If they're pure elements in there, you have to use coefficients. And the coefficients are there to change the numbers of whatever comes after them, compound or simple elements. For instance, if we were to write what happens in the space shuttle engine when it fires up? Well, there's hydrogen coming out of that big orange tank, and there's oxygen coming out of that big orange tank. And when they meet, they get really hot, really fast, and they make water. Okay? So we know that this is what comes out, this is what's mixed with that for the reactants, and this is the product. Well, you can see right off, the hydrogens are balanced, but the oxygens aren't. Right? So how do you get 2 oxygens over here? We can't change the formula of water. That's fixed. So if we put a 2 in front, that means now we have 2 oxygens here. But we also have 4 hydrogens. So we got the oxygens fixed. Now we got to come back over here and say 4 hydrogens. Now it's balanced because we got 4 hydrogens there, 4 hydrogens there, 2 oxygens here, and 2 oxygens there. That's a balanced equation. And once you've balanced an equation, the ratio of reactant to product is fixed. It can be used as a conversion factor. 2 hydrogens equals 1 oxygen, or 2 hydrogens equals 2 waters, or 1 oxygen equals 2. You can think of it in those terms if we use it as a conversion factor. Okay. I think these guidelines came out of your textbook. I'm not going to sit there and talk about them. I think we just need to balance a few equations using my budgeting method. These are rules. Subscripts can't be changed. You can only change coefficients. And you want the smallest whole number ratio. Now, the ratio of hydrogen to oxygen to water is 2:1:2. Technically, it could be 4:4, be the same ratio, but we want the simplest whole number ratio. So if we said 4:4, you could divide each one of those by 2. So 2:1:2 is the simplest whole number ratio for coefficients. In general, what we want to do, and you'll be given this, what are the reactants? What are the products? And sometimes the physical state is necessary. In this case, this is a gas, right? So we use a parentheses with a little g. This is a gas. And at those temperatures, that's probably a gas too. But that is usually stated in the problem. What are the states of the reactants and products? All right, these are my helpful hints. And this is my budgeting method. What I've found in most chemistry books, most introductory chemistry books or most general chemistry books is when they get to this part where you balance equations, they will simply say, after they've given you those rules, they'll say balance by inspection, right? Which means absolutely nothing. So I worked on this method, and it's pretty reliable. I call it my budgeting method. I'm going to show it to you in just a second. But these are some helpful hints, and they're included in one of those documents. Balancing equations. There it is right there. Balancing chemical equations, helpful hints. You don't always use every one of those for every situation. Those are situations where the hints will help you. And I'm going to go through them as we talk about it. So let's use this example. C6H12O6. C6H12O6. That's glucose, right? The same stuff that circulates in your blood and takes energy from one place to another and dumps it off at your cells so that they can function, right? And that's what insulin's for. It makes the cells able to use that glucose. So if you're diabetic, that's the molecule that accumulates in your blood and goes like that. But we add oxygen to it, right? In the cells, this overall reaction happens in multiple steps, right? But you can take glucose in a spoon, or table sugar for that matter, which is a different formula, but you can light it with a cigarette lighter and it'll burn and it'll go through the same reaction. But in your cells, they're taking this stepwise. That way they don't release all their energy at once and destroy the cell process. Okay, so what do we have left? Well, you end up with carbon dioxide and water. Okay. Now, this is a solid. We'll just do that. This is a gas. This is a gas. This is a liquid. Okay. To balance an equation like this, my budgeting method says that you take each one of the elements in that equation and you set it up down the side here. So we got carbon, hydrogen, and oxygen. Okay. How many do you have on this side? This is your starting point. We have 6 carbons here. We have hydrogens, 12 of them. We have 6 plus 2 is 8 oxygens. On this side, we have 1 carbon. And hydrogens, we have 2 hydrogens. And oxygens, we have 3. Okay, that's where you start. Using this budgeting method, then as we add coefficients, we'll change these values to reflect the changes. And that way you can see instantly whether you have the same number on each side. Okay, it keeps track of them for you. Sometimes I go through and add them up and I say, okay, 2, 8, 26. So there's 12 and that's 26. Okay, just to check myself, see if I accounted for everybody. Okay, so the next question is, where do you start? Right? Which element do you do first? Well, sometimes that takes a little intuition, but there's one place you don't start. You don't start with free elements. I mean, this is oxygen by itself. We save it to last. And the reason we save it to last is if you put a coefficient in front of this, it only changes oxygen. If you put a coefficient of this, it'll change carbon, hydrogen, and oxygen. Right? And if you start here and go there, you're going to go around and around and around, and you keep changing. Eventually you'll get there, but it'll take you a while. So save these elements to last. And we save water till next to the last. All right. So if you can't decide, just start at the top. 6 carbons there. I want 6 carbons here. Okay. So that changes this to 6. changes that to 12 plus 1 is 13 oxygens. You may have noticed 13 and 8, that's kind of an odd, you got even, odd, even number there, odd number here. Sometimes they work out on their own, and you don't have to use any tricks. So we're gonna wait and do the tricks later. Okay, so now we have carbons are good. How about hydrogens? Well, let's see. We got 12 hydrogens there. Hydrogen only occurs in one place over here. So if we put a 6 here, that gives us 12 hydrogens, doesn't it? And it also gives us 6 oxygens and 12, 18. Correct? 18 oxygens on this side. 6 plus 12 is 18. Now we've got 2 places for oxygen over here. So how many more oxygens do we need? Well, we've got 6 oxygens here. So 6 from 18 is 12. We need 12 more oxygens, don't we? What if we put a 6 there? That's 12 plus 6 is 18. Now we're balanced. Okay. I try to make this as methodical as possible, but there is an element of intuition involved. Recognizing patterns. This one is a hydrocarbon, CH203. And if you drove your car today, you burned a bunch of it. That's octane. That's the primary component in your gasoline. And this is what happens in your engine. Plus oxygen yields carbon dioxide and water. Unfortunately, it's not just oxygen that goes in there. There's nitrogen and some other things. And incomplete combustion yields some pollutants, right? Incomplete carbon monoxide, oxides of nitrogen. That's what your catalytic converter does. It takes those and completes the reactions. But that's another topic. Okay, let's see how we're doing on time. Want to be sure. And okay. Okay, we still got stoichiometry to do. Sometimes, in this case, sometimes you save your oxygen till last, but a whole number in front of that oxygen will not give you the right number of oxygens to complete the budget. So in this case, we used a fraction. We needed 25 oxygens on the reactant side. So we did 25 halves of O2, right? A half of an oxygen molecule is 1 oxygen times 25 is 25 oxygens. Once you've determined, once you balance the equation with this fraction, then you want to get rid of the fraction because we want whole numbers only. So how do you get rid of a fraction with a 2 in the denominator? You multiply by 2. Once it's balanced, once the equation is balanced with that fraction, then the ratios are set. 1 octane, 25 halves of oxygen, 8 carbon dioxides, and 9 waters. So if you multiply the entire equation through by 2, you don't change the ratio. The ratio is fixed now because it's balanced. But if you multiply through by 2, now you get 2 octanes. And we get rid of the 2 in front of the oxygen. Now it's 25 halves, 25 oxygen molecules, 16 carbon dioxide, and 18 water. That's one of the tricks. The helpful hints is sometimes you can use a fraction as an intermediate step. This one, sometimes it crops up. If you have an equation where let's see. An element occurs on one side, on both sides of the arrow, but let's see, hydrogens. We're focusing on hydrogens here. Look here, you've got 3 hydrogens on this side and 2 on this side. So sometimes you have to use 2 coefficients at the same time. And if you've got an odd and an even, that can be a problem. So in this case, I used a trick from math. It's called cross multiplication. So you take the 2 coefficient from hydrogen and you put it over here in front of the ammonia. And you take the 3 from this hydrogen and put it in front of the water. So that means that now you have 6 hydrogens on one side and 6 hydrogens on the other. Okay. That's another trick. You don't always have to use that. Sometimes you'll make a false start with your budget and say, wait a minute, this thing is not working. So go back and look at it and say, maybe this trick will work. Go back and do it. The number 7 here, you'll notice that these compounds have polyatomic ions in them. If the polyatomic ion remains intact through the reaction, in this case, you've got ammonia on the left and ammonia on the right, ammonium on the right. It didn't break apart, right? The nitrogen and the hydrogen are still together. You can use that as a balancing unit. Rather than put the individual elements, you can save yourself headache by just using that ammonium as a balancing item in your budget. Phosphate's the same way. So I've set it up down here. Notice that there's ammonia, phosphate, calcium, and chlorine. And these are the initial amounts. Right? On the left-hand side, 3, 1, 1, 2, and on the right-hand side, 1, 2, 3, 1. And then you go through and use your budget. Right? In this case, we don't have any individual elements, so you don't hold those to the end. So you just pick a place to start. I think I started with calciums. Right? So that's a 3 in front of that calcium gives me 3 calciums on the left and 3 calciums on the right. And then I'm going to balance the ammonias. Right? So that's step 1, step 2. Step 1 here, step 2 there. Oops. And then step 3, I'm going to use a 2 in front of the ammonium phosphate. And let's see, 6, 2, 3, 6. It's balanced. And you can see instantly from those blue numbers that your equation is balanced. All right. So the only point here is that you may have more than one of these that are technically balanced, but they're not all whole numbers. We want whole numbers, not fractions, not anything that can be divided by a common denominator. So Roman numeral 2 is the best answer for that one. All right, I'm going to have to skip this. I better not. The number of molecules in a balanced equation, the number of molecules is conserved? No, not necessarily. If you have the same number of molecules on both sides, it's purely coincidence. The coefficients tell you how much of each substance you have. That wording is poor. How much means mass. It doesn't tell you anything about the mass. It tells you about numbers of atoms and numbers of molecules that go into the reaction. Atoms are neither created nor destroyed. That's true. You have the same number of atoms of each element on the reactant side and the product side. Coefficients do not indicate mass ratios. They indicate mole ratios. And the sum of the coefficients on the reactant side doesn't necessarily equal the sum of the coefficients on the product side. So don't be looking for that. All right. I'm going to have to let that one go. We'll have to do some balancing equations from the review document when I get back 2 weeks from today. So you got plenty of time to work on them. So the meaning of these coefficients can either be individual, it can be 4 moles of iron or 4 atoms of iron, combined with 3 moles of oxygen gas or 3 atoms of oxygen gas, 3 molecules of oxygen gas. And remember, if the word problem says hydrogen reacts with oxygen to produce water, remember your diatomic elements. That's diatomic. That's diatomic. So when you write the equation, you better write it this way. If you don't write it that way, it'll never balance. Or it won't be correct anyway. So that's why I emphasize those. When you were memorizing those symbols, I had some of them that were highlighted in blue. Those are the diatomics, right? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of those are diatomic. So if a reaction says one of those is reacted with something else, always write it diatomic. All right. So what we're talking about here is mole ratios of reactants and products using those coefficients. And as a consequence, you can write a conversion factor for each one. Right? 4 moles of iron produces 2 moles of iron 3 oxide. So that's 4 moles on top of iron and 2 moles of iron 3 oxide on the bottom. That's a conversion factor. We're going to use one in just a minute. Right? So in this case, we have to balance the equation first, right? You can see right off, there's only 1 carbon on the right and 2 carbons on the left, so we would have to balance that. Right? And I don't have time to do that, but if you do, the ratio is, the coefficients are 2, 7, 4, and 6. And this is one of those equations where you use the fraction trick. At some point, you need 7 halves of oxygen, and then you multiply times 2 to get rid of the fraction. All these are called hydrocarbons, where you have carbon and hydrogen together like that. That's a hydrocarbon. All hydrocarbons use that fraction when they're burned in oxygen, except for one. Methane. Methane doesn't need that trick, but the rest of them do. All of them do. So any hydrocarbon with oxygen producing carbon dioxide and water, you're going to need that fraction trick. All right, stoichiometry. Stoichiometry is the method of using a balanced equation and amounts. In our case, we're going to start off with masses. Masses of reactants to say how much product is produced. Right? Because we don't measure things in numbers of atoms. We don't have any instruments in the lab that'll do that. So we have to measure in mass. But the reaction itself is based upon numbers of atoms and numbers of molecules. So we're forced to go from mass to molecules and then conduct the reaction to find out how many molecules of product, and then change the molecules of product back to mass. That's the idea behind stoichiometry. They started off with a bad one here. This is too much. But it is what it is. Let's do it. Methane reacts with oxygen. So this is our first reaction. Methane reacts with oxygen to produce what? Carbon dioxide and water? Yep. Notice I left space for coefficients. All right, so let's balance this one and then we'll do the second one. All right, let's do our budget. Some of these equations, you may find it easier not to do the budget. I mean, you can see the balancing off, but for practice, let's do the budget. Carbon, hydrogen, oxygen. 1 carbon, 4 hydrogens, 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens. Okay. Carbons are already good. Hydrogens, we've got 4 hydrogens, we need 4 over here. So that's 4 hydrogens, that makes 2 and 2, or 4 oxygens. We saved this oxygen to last. Now we need 2 in front of that to give us 4. That equation's balanced. Okay. Now let's do the other one. Ammonia, NH3. Plus what? Reacts with oxygen to produce what? Nitrogen monoxide plus water. Okay, so we set up our budget. There's nitrogen, hydrogen, oxygen. 1 nitrogen here, 3 hydrogens, 2 oxygens. On this side, we have 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay, nitrogen's already balanced, so we'll go to the hydrogens and see what they do. So we've got hydrogen in one place over here and one place over here. This one has 2 hydrogens and this one has 3. So we're going to use the cross multiplication trick. We're going to take that 2 and put it over here, and take that 3 and put it over here. So now we have 6 hydrogens on both sides. But over here, we also changed the number of oxygens. 3 plus 1 is 4. And on this side, we changed the number of nitrogens. Okay. So now we need 2 nitrogens here. But that changed oxygens again. Right? 2 plus 3 is 5. Okay. All right. So we got nitrogen and hydrogen balanced. How do we fix oxygen? Right. We got 5 on that side, 2 on this side. We need 5 on this side. Right. So we say 5 halves. So 5 halves of an oxygen molecule is 5 oxygens. Right? Half of an O, right? Half of that is 1 times 5. So that's why 5 halves works. But we want whole numbers now. It's balanced. Right now, technically it's balanced. We have the same number on both sides, but we want whole numbers. So we're going to multiply the whole thing through by 2. So that we can get rid of that 2, right? 2 times 5 halves is 5. So we're going to change that to 5. Change this one to 4. Change this one to 4. And change this one to 6. There we go. Now we've got 2 balanced equations. What's the question? Well, the first one was write the balanced equations. Okay, so we did that. There we go. 4, 6, 5. Okay. I am in agreement with the slide. That's good. Now the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? All right, so we got all the oxygen we need. We don't have to worry about that one. We'll use up all the oxygen that's available and consume everything that's given. 1 gram of methane. All right. What the end result is, what's mass of ammonia? how many grams of ammonia will give us exactly the same amount of water as 1 gram of methane. So the number of moles of this one has to equal the number of moles of that one. Exactly the same amount. Okay. So we need to find out, first of all, how many moles of water will that 1 gram of methane produce. Okay. Here's another rule. Right? We got lots of rules. You can't go anywhere in that equation with mass. It will not work. Just think of it as there's a big wall here and a wall here and a wall here. You can't get over that wall with mass. You have to have moles. So we got to convert that to moles. How many moles of methane are going to be reacted? So how do we do that? Well, we need a conversion factor that will get rid of grams and leave us with moles, right? There's that quotient again, grams and moles. So what's the molar mass of methane? Well, let's see. Carbon is 12.01. And hydrogen is 1.01 times 4. So that's 1605. That's the molar mass of methane. And that'll give us the number of moles of methane that we start with. Then we can move. All right, so I'm going to divide 1605 into 1, and that's 0.0623 moles of methane. All right. So how do we get from moles of methane to moles of water? We use coefficients. Coefficients will create for us a conversion factor. If this is moles of methane, then the ratio of the two is moles of methane here, moles of water here. What's the ratio of the two? There's a 1 right here. And there's a 2 right there. So for every 1 mole of methane, you produce 2 moles of water. And this will cancel moles of methane and leave us with moles of water. Right? So I just need to multiply by 2. 0.1246. Okay. Now at this point, if the question were not stated the way it was, if it was just asked of you what mass of water is produced, then you would take that number of moles and convert it back to mass. Right? Molar mass, grams per mole, cancels the moles and leaves you with grams. 18.02 times that will give you the mass of water. Okay, if that were the question. But that's not. What we want is 0.1246 moles of water from this reaction. The same number of moles, exactly the same number. But we want to work backwards now. Right? So I'm gonna do my conversion factors backwards. Right? We want moles of water, and now we want moles of ammonia. How many moles of ammonia would produce that many moles of water? What's the ratio? 6 water and 4 ammonia. So 4/6 of that is 0.0831. And that's moles of ammonia. Right? We canceled this one right there, left us with moles of ammonia. Now we can convert to grams of ammonia. We know how many moles. We need a conversion factor that will cancel moles and leave us with grams. Okay? This is in the denominator, that's in the numerator. So what's the molar mass of ammonia? Let's see. Nitrogen is 14.01. And we have 3 hydrogens. 3 times 1.01. 1704. So 17.04 times that value will give us 1.4. Let's see, how many Three significant figures. 1.42. So what we're saying is 1.42 grams of ammonia combines with oxygen to give you exactly the same number of moles of water as 1 gram of methane does when it combines with oxygen. Okay. Did you follow me or did I lose you? This is all dimensional analysis, conversion factors. Once you get the equations balanced, then it's back to chapter 2 or 3, whichever one it was where we did dimensional analysis. That's stoichiometry. And let's see, I think it's animated. Yeah, there we go. So that's the moles. That's scientific notation for what I had up here. And then change it to moles of water. And then we take moles of water, convert it to moles of ammonia, and then convert moles of ammonia to grams of ammonia. And that answers our question. All right, one last thing. I think I got time to talk about this. Yeah. Yield, the concept of yield. If you're a chemist working for a company, especially, a chemical engineer, and the bottom line, the profit that company can make off of a chemical reaction is based upon how much product you can produce from that chemical reaction. You know the chemistry, right? Your lab chemists have given you the reaction. Now you got to scale it up. You need to know something about, okay, if I go through this process and I do this and this and this and this, and isolate the product when it comes out, how much of that product do I get compared to what the theory or the balanced equation says I should get? Right? The balanced equation and the stoichiometry from that equation tells you that's 100%. Right? So that calculation we just did would be 100% conversion, no losses at all. The fact of the matter is, when you actually do these reactions in real life, you lose some. Right? So, and it could be from things like side reactions, right? We've written the equation here, that's the one we want, but lots of times you get side reactions that steal your reactants into a different product that you don't want. Or when you isolate the product from the mixture, you don't get 100% yield. You don't extract all of the product that's produced from that. So you have losses. That's the actual yield. So if we ratio the actual yield to the theoretical yield here in this equation, multiply by 100, we get a percent yield. Some reactions, if you can get 15% yield, that's good. In fact, that was Fritz Haber's outcome, converting nitrogen with hydrogen to make ammonia. He eventually got to 15%, and that was great. Some reactions, you can get 90% or better. But you have to take that into account when you're actually producing a product. And the higher the yield, the better. And the happier your supervisors are if you can do it as a chemical engineer. Okay, what would be the percentage yield of a product for a chemical reaction where the theoretical yield and the actual yield are these? 5.6 is the theoretical, 4.5 is the actual. 5.6 grams, 4.5 is the actual times 100. That's the calculation. And it's probably in the neighborhood of 80%. Yep. Now, it's possible to get more than 100%. If you do that, that means you've got contamination, right? Because you're not going to get more than 100% product. All right. Let's see. Yeah, we got a few minutes. We can do one of these anyway. I think there are two of them. Concept checks. Yeah. So let's do this one. Pennies produced prior to 1982 were composed of 95% copper. That's true. Anything after 1982 on, the currency was debased. That's the proper term for it. It was made cheaper. And the way they did it was the blanks were made out of zinc, which is a lot cheaper than copper. And they just covered the zinc blanks with copper, an outside layer. So on average, these actual copper pennies weighed 3.11 grams. How many atoms of copper were present in one pre-1982 penny? Okay, so if you've got 3.11 grams, 3.11 grams is the total weight, but only 95% of that is copper. Then we need that fraction, 0.95 is the fraction that's actually copper. So we'll do that one first. 2.95, 2.95. So that's how many grams of copper you have. From there on, how many atoms? Right? It's just convert grams of copper to moles. Right? I should remember that. 6355. Okay, that gets rid of grams and leaves us with moles. Now we can cancel moles and leave us with atoms. If we know the conversion factor, 6.022 times 10 to the 23rd. Right? So that's the thinking part. The rest is crunching numbers. So we'll take that divided by 63 point. Oops, try it again. And then 6.022 times 10 to the 23rd is 2.80. 2.80 times 10 to the 22nd atoms. There we go. There should be another significant figure in there, shouldn't there? Because we started off with 3.11, 2.80. All right. So we have time to do this one. 2-liter bottle of carbonated soda has an equivalent, excuse me, I got to move this out of the way. On an equivalent average, 0.2 grams of glucose per 100 milliliters. Glucose is metabolized in the human body according to that reaction. Use the following steps and the associated equations to determine the number of grams of CO2 produced after the consumption of 10 2-liter bottles. Okay. We've balanced the equation before. But that's the same equation we balanced earlier. It's the ratio of 1:666 for each of the reactants and products. What you're given is 0.2 grams of glucose per 100 milliliters. Right? So how many milliliters is 10 bottles of 2 liters? Right? 2-liter bottle is 2,000 milliliters. So 2,000 milliliters right here, well, times 10, so that'd be 20,000 milliliters. This part of the problem would give us how many grams of glucose. Then we convert grams to moles. of glucose. And then with the balanced equation, we know that 6 moles of CO2 for every 1 mole of glucose. So that gives us, let's see, is it going to do cancellation for me? No, it's not. That gives us, this part of the equation now gives us how many moles of CO2, and we convert that to grams. And it turns out 59 grams of CO2. If you drink that many bottles of pop, you'll exhale 59 grams of carbon dioxide. All right, so we're done with that.